We talked about quantum numbers, but an important part of quantum numbers that we need to talk about is nodes. So we already talked about how nodes are a region of zero electron density, or region of zero probability of electron density. If you know your principal quantum number for your atomic orbital, then you know your total number of nodes. So if your total number of nodes is just your principal quantum number minus 1. And remember that we talked about how there's two different types of nodes. There's angular nodes and radial nodes. And we talked about how angular momentum quantum number is your number of angular nodes. And so n minus L minus 1 is your number of radial nodes. I just wanted to look at a couple examples of different types of nodes to figure out how many radial nodes are in a particular orbital. So here are some examples of a 1s, 2s, and 3s orbital. And for an s orbital, L is equal to 0, so there are 0 angular nodes. For an s orbital, L is equal to 0, so there are 0 angular nodes. But if your n is greater than 1, then an s orbital will have radial nodes. So here's some examples. This is a 1s orbital, a 2s orbital, and a 3s orbital. So the 1s orbital doesn't have any radial nodes. The 2s orbital has 1 radial node, and the 3s orbital has 2 radial nodes. So I just wanted, and then here's some 3p orbitals. This is a 5d orbital. So just to reiterate, 1s orbital, n is 1, L is 0, so your radial nodes is 1 minus 0 minus 1, which is 0. If you have a 2s orbital, n is equal to 2, L is equal to 0, so your radial nodes is 2 minus 0 minus 1, so it's 1. And then finally, this is our 3s orbital. N is equal to 3, L is equal to 0, so your total number of radial nodes is 3 minus 0 minus 1, which is 2. For our 3p orbital, n is equal to 3, and now L is equal to 1, right? We have 1 angular node bisecting the orbital. So your total number of radial nodes will be 3 minus 1 minus 1, which is 1. So we have 1 radial node and 1 angular node. We have 2 total nodes, which makes sense because n minus 1, which is 2, is our total number of nodes. And finally, this is a 5d orbital. So here we have L is equal to 2. We have 2 angular nodes. So n is 5, L is 2, so our radial nodes is 5 minus 2 minus 1, which is 2. So we have 2 radial nodes for a 5d orbital. Okay, so here's just a couple more examples identifying incorrect quantum numbers. So what is wrong with each of the following quantum numbers, designations, or sublevel names? Okay, so let's look at this first one, A. N is 1, L is 1. Okay, well the problem here is that the rules for the angular momentum quantum number is that they can only be 0 up to n minus 1. So a 1p orbital just simply cannot exist. All right, let's look at B. So we have n is 4, L is 3, and we have m sub L is plus 1. Okay, so all of these quantum numbers are allowed. The problem here is the name. So if L is equal to 3, this is actually an f orbital, not a d orbital. So this should be a 4f. This orbital should be in the 4f sublevel. Okay, finally, n is 3, L is 1, so this is a 3p orbital. The problem with this is that m sub L can only range from negative L to L, so you can't have m sub L negative 2 for a 3p orbital.